Welcome to this in-depth lecture on microcapsules, engineered cells that revolutionize drug delivery, food science, and materials engineering. Think of microcapsules as eggs with programmable shells, a protected core surrounded by a carefully engineered barrier that controls release. Let's start by understanding what microcapsules are and why they matter. Microcapsules are tiny spherical containers ranging from 1 to 1,000 micrometers in diameter, about the width of a human hair. The core can contain drugs, flavors, dyes, or reactive chemicals that need protection or controlled release. The shell is a barrier made from polymers, lipids, or proteins that protects and controls release. Microcapsules come in various sizes, from 1 micrometer for drug delivery to 100 micrometers for food applications. The shell material determines how the capsule behaves under different conditions. Polymers like polyamides and polyurethanes provide mechanical strength and chemical resistance. Polymer chains interlock to form strong, flexible shells with tunable permeability. Lipids, especially phospholipids, naturally assemble into bilayer membranes, similar to cell membranes. Lipid bilayers create biocompatible shells, perfect for drug delivery and mimicking biological membranes. Proteins like albumin and gelatin offer biodegradability and natural compatibility with biological systems. One key method for creating microcapsules is interfacial polymerization at the droplet surface. First, we create an emulsion where oil droplets containing our core material are dispersed in water. Oil droplets containing active ingredients float in a continuous water phase stabilized by surfactants. Next, we add reactive monomers to both the oil and water phases that will meet at the interface. When the monomers meet at the droplet surface, they react and polymerize, forming a solid shell. The polymer shell forms spontaneously at the interface, encapsulating the core material in a protective barrier. This reaction between two monomers creates the polymer network that becomes our capsule shell. Another powerful technique is layer-by-layer assembly, building shells one molecular layer at a time. We alternate deposition of positively and negatively charged polymers, building up layers through electrostatic attraction. Each layer adds about 1 nanometer of thickness, allowing precise control over shell properties and permeability. This technique gives nanometer scale precision in shell thickness and composition. Now let's understand the mechanical behavior of these thin shells using continuum mechanics. The Laplace law is fundamental for understanding how pressure differences are balanced by shell tension. Delta P equals 2 gamma over R, where gamma is surface tension and R is capsule radius. For elastic shells, we must relate tension to the material's elastic modulus and shell thickness. Gamma equals E times H times epsilon, where E is elastic modulus, H is shell thickness, and epsilon is strain. Combining these, pressure difference equals 2 EH epsilon over R. Shells buckle when compressed beyond a critical pressure, determined by geometry and elasticity. Critical pressure is approximately EH squared over R squared times 1 minus nu squared, where nu is Poisson ratio. Let's solve a practical design problem. How thick must a capsule wall be to survive blood flow but break in the stomach? In blood vessels, capsules experience shear stresses of 1 to 10 pascals from flowing blood. In the stomach, capsules face both acidic conditions and mechanical pressure of 100 to 1,000 pascals from churning. Let's do an order of magnitude calculation to estimate the required shell thickness. Assume capsule radius of 100 micrometers, which is 10 to the minus 4 meters. Typical polymer elastic modulus is around 1 gigapascal or 10 to the 9 pascals. Blood pressure is 10 pascals. Stomach pressure is 500 pascals. From our earlier equation, shell thickness H equals pressure times radius over 2E times yield strain. Assume yield strain of about 0.1 or 10% elongation before failure. For blood flow, we need thickness of about 5 nanometers to avoid deformation. For stomach rupture at 500 pascals, we need shells thinner than 250 nanometers. Therefore, a shell thickness between 50 and 200 nanometers would survive blood flow but rupture in the stomach. This design window ensures the capsule survives circulation, but releases its contents in the digestive system. Let's analyze how capsules rupture when subjected to hydrodynamic forces in flowing fluids. In shear flow, capsules deform from spheres into ellipsoids, creating stress concentrations. Under shear flow, the spherical capsule deforms into an ellipsoid, with maximum stress at the poles. The capillary number Ca equals viscosity mu times shear rate gamma dot times radius over surface tension. For capillary numbers less than 0.1, deformation is small and capsules remain stable. When capillary number exceeds 1, deformation becomes large and rupture becomes likely. Critical stress for rupture is approximately EH over R, proportional to elastic modulus and thickness. Let's work through a complete numerical example for a drug delivery capsule. Consider a 5 micrometer radius capsule with 100 nanometer thick shell. Shell modulus is 500 megapascals. Blood viscosity is 3 millipascal seconds. In arterial flow, shear rate is about 1,000 per second. Effective surface tension is 10 to the 4 newtons per meter. Capillary number is only 1.5 times 10 to the minus 6, much less than 1. With such a low capillary number, this capsule will easily survive arterial blood flow without rupturing. Now let's examine what happens when capsules are compressed between surfaces. A common test is compressing capsules between parallel plates to measure mechanical properties. Capsules compressed between plates first flatten, then buckle when critical pressure is exceeded. Compression force equals 4 pi EH squared over R times 1 minus nu squared times displacement delta. Buckling instability occurs when parts of the shell experience compressive stress. Buckling pressure is 2 EH squared over R squared times square root of 3 times 1 minus nu squared. Let's calculate buckling pressure for a typical capsule. Buckling pressure is approximately 4,700 pascals, easily exceeded by finger pressure. Microcapsules revolutionize drug delivery by enabling targeted and controlled release. Capsules can be designed to accumulate at specific disease sites through size selection or surface modification. After injection, capsules travel through circulation and release their drug payload at the target site. Release can occur through slow diffusion through the shell or rapid rupture triggered by pH, temperature, or enzymes. The shell protects sensitive drugs from degradation in the bloodstream until they reach their target. Diffusive release rate equals diffusion coefficient D times concentration difference over shell thickness H. In food science, microcapsules protect flavors, vitamins, and active ingredients. Encapsulating flavors prevents evaporation and oxidation, preserving taste until consumption. Probiotic bacteria can be encapsulated to survive stomach acid and release in the intestines. When you bite a food product, mechanical stress ruptures the capsules, releasing intense bursts of flavor. Vitamins like vitamin C are protected from oxidation, maintaining potency during storage. Self-healing materials use microcapsules filled with repair agents that activate upon damage. Capsules containing liquid monomers or adhesives are embedded throughout the material matrix. When a crack propagates through the material, it ruptures capsules, releasing healing agent that flows into the crack. The mechanical stress from crack propagation ruptures nearby capsules automatically. The released monomer contacts a catalyst in the matrix and polymerizes, sealing the crack. Healing efficiency is the ratio of healed strength to original virgin material strength. Real self-healing systems can recover 60 to 90% of the original material strength. Advanced designs include multi-core capsules for sequential release or triggered reactions. Multi-core capsules contain separate compartments with different active ingredients for complex release profiles. This enables sequential delivery of multiple drugs or controlled mixing of reactive components. Let's summarize the key design parameters that engineers must balance. Engineers must optimize capsule size, shell thickness, material choice, and release trigger mechanism. Optimal thickness H equals radius times square root of trigger pressure over elastic modulus. There's always a trade-off between capsule stability during storage and ease of release at the target. Despite advances, manufacturing consistent microcapsules at scale remains challenging. Producing capsules with narrow size distribution is difficult, but critical for consistent performance. Shell uniformity is essential because even small defects can cause premature rupture. Scaling up production while maintaining quality control presents significant engineering challenges. Advanced manufacturing techniques like Microfluidics can produce highly uniform capsules, but at lower throughput. The field continues to evolve with exciting new directions and applications. Future capsules will respond to multiple simultaneous triggers like pH plus temperature plus light. Capsules could detect disease biomarkers and automatically release therapeutic agents in response. Some researchers are creating artificial cells where encapsulated enzymes perform metabolic reactions. Future smart capsules will integrate multiple sensing and response mechanisms in a single platform. Let's summarize the key concepts from this comprehensive lecture. Microcapsules function as engineered cells with shells we can design for specific applications. We can choose from polymers for strength, lipids for biocompatibility, or proteins for biodegradability. Main fabrication methods are interfacial polymerization for speed, or layer by layer for precision. The mechanical behavior is governed by thin shell theory, Laplace law, and buckling instabilities. Successful design requires carefully balancing stability during storage with ease of release at the target. Applications span from targeted drug delivery to flavor encapsulation to self-healing materials. Microcapsules are versatile platforms for a wide range of applications.